Some of our older products used to have little screens that showed current network usage. Their practicality was questionable, but some people really missed them. So I wanted to give you a little project idea. You can make your own screen. With our REST API, it is actually pretty easy. You're not limited to the device or the programming language. I might even do a little project that runs on your computer or container using Python or JavaScript. But for this video, we're using an ESP32 with an LCD screen. The particular brand implementation doesn't matter too much, as long as you can make HTTP requests to your router and then draw lines on the screen, you're probably good. At first, I got this 7-inch touchscreen because it was one of the bigger options out there. But then I realized that I would have to use this LVGL library, which seems to be a very good tool if you want to create a modern looking GUI, but is a complete overkill for this super simplistic, old school monitor idea I wanted to make. So I ended up using this scratched up SPI controlled screen instead. As you can see, it is displaying a simple graph for TX and RX values. It is just for a single interface right now, but if you have some controls, you could easily adapt this where you can flip through all of your interfaces or just display a table instead of a graph. Now, at the very core of my little project is actually a single REST API command. Here it is. It's just a POST request connecting to the router and essentially executing Ethernet print command. Let's paste this into a terminal. And here's the result. It looks like a mess right now, but it's actually JSON format, so you could easily convert that to something more readable. Let's save the output as an actual JSON file. Now if I open this with a browser, that's a lot more readable. Here is the first entry, which is for Ethernet 1. And if we scroll down, we can see that there is RX bytes value and TX bytes value. We can use those values to calculate the exact network usage. It is actually more accurate than the interface monitor tool because the values on the monitor can fluctuate very rapidly and we're only making one request per second, so we wouldn't be seeing the full picture. Now I'll quickly go over my code, explain what it does. You can use it in your project if you want. It's on GitHub. We start off by including all the libraries. TFT ESPI is what's actually going to do the drawing on the screen. Then we declare screen size as constant values because they're not going to change. And we calculate history size, which is going to be the amount of data points that we're going to fit inside the screen width. We'll be using 4 pixels for each TX-RX data point pair. Then we declare the values necessary to connect to our router and the graph interface value, which is the ID for the interface that we're going to be actually graphing. Ethernet 1 is usually going to have ID value of 1, but it could vary between routers. Then we create a struct to contain all the information that we have to store for each interface. The important parts are the 2 arrays containing the data points for the graph. Then we create a map for those interfaces. We could also create an array, but a map is more malleable. We only have one function that converts the string value of an ID to an integer. The void setup initiates the screen and then initiates the Wi-Fi. Moving on to the main loop, we open up an HTTP connection to our router and send the REST API command for Ethernet print. We take the response in JSON format and loop through it. Record the ID, RX, TX values and the interface name. They're also printed in the serial terminal. If you want to find out an ID for another interface other than Ether1, you'll be able to do that through the terminal. Then as we loop through the interfaces in the JSON file, we take their IDs and check if they're already found on the interface map. If they're not there, a new interface is added to the map, and if it's already there, it's simply selected for further data storage. All the values stored in the struct are calculated and stored there, And then finally, we can move on to the part where we do the actual drawing. First, we loop through all the data point values that we're going to be using for graphing and determine the biggest values so that we can scale the graph down to fit in our screen. We loop through our screen width 4 pixels at a time and move on in our data points with every loop. Then we use the map command to determine the actual pixel values that we're going to use for drawing. And then finally draw little rectangles. Calculate the megabits per second values and draw text in the corner of the screen. And the very last action is a delay of 1 second. Now you might realize that all the drawing and the previous calculations took up some time already. So the total for one loop is going to be slightly more than 1 second. But that only affects the refresh rate of our graph because we're using this milliseconds function, which gives us exact milliseconds elapsed that we use for our calculations. So all the megabits per second values are absolutely 100% correct. As I said before, this code can be found on my GitHub. Feel free to use it, and I'll see you next time.